In this video, let's learn how to diagonalize a matrix. So if we're given a matrix 3, 1, 2, 4, we want to write it in the form P times some diagonal matrix times P inverse. So basically our job is to find what P and D are. The first steps to solving these kinds of problems is identifying the eigenvalues of the matrix, and then we're going to find the eigenvectors in each of those eigenspaces, and that will allow us to make the diagonal matrix, and that's about it. So let's start off and do the determinant of A minus lambda I is equal to 0. This is better known as the characteristic equation, and this allows us to find the eigenvalues. So if we did that, we have that 3 minus lambda, 1, 2, and 4 minus lambda, and we want to find the determinant of that. So that's going to be equal to 3 minus lambda times 4 minus lambda minus 2 is equal to 0. So if we expand this out, we're going to get 3 times 4, which is 12. 3 times negative lambda equals negative 3 lambda. Negative 4 times lambda is equal to negative 4 lambda. And then negative lambda times lambda equals lambda squared minus 2. And so we're going to get lambda squared minus 7 lambda. And then 2 takes that 2 out, and we're left with plus 10. And that's going to be equal to 0. So let's go ahead and factor that out. We want two things to multiply to 10 and add to negative 7. So let's do negative 5 and negative 2. And that adds to negative 7. So this is going to factor into lambda minus 5 and lambda minus 2. That's all going to be equal to 0. So one eigenvalue is going to be lambda equals 5, and the other one is going to be lambda is equal to 2. And from here, we can quickly write our D matrix, which is just going to look like this. I'm going to put the lambda equals 5 eigenvalue right here. Let's call that lambda 1, and let's call this lambda 2. And I'm going to put the lambda 2 value right here. And on the off diagonals, I'm going to put zeros, and that's going to be our D. Next step is to find the eigenvectors that correspond with these eigenvalues. So let's see how we would do that. So we apply that, finding the eigenvalues or vectors, like I showed in a different video, is looking at the null space of A minus lambda I, and we'll get something that's like span of some vector. And that vector is going to be our eigenvector. So let's go ahead and try that out. First, let's plug in our value of lambda 1 equals 5. So we do null of A minus 5i. And so that vector, or that matrix, is going to look like 3 minus 5, 1, 2, and 4 minus 5, which is equal to negative 2, 1, negative 1, 2. And so what we're going to do is find the null space of this. So that's like, let's go ahead and augment it with 0. Some people don't even augment it. They just start row reducing. So I'm going to avoid this column because everything we do row reduction wise is going to keep that the same. If I do replacement, just add row 1 to row 2 and put in row 2, we get 2, 1, 0, 0. And remember, this is going to be equal to, there's going to be like x1, x2, and that's going to be equal to the 0 vector. So now we can row reduce it more. Let's divide by negative 1/2, or scale by negative 1/2. We get 1 and negative 1/2, and then 0, 0. If we rewrite this in parametric vector form, we have x1 equals negative x2. Writing the basic variables in terms of the free variables is going to be minus or plus 1/2 x2, and then x2 is just going to be equal to x2. And now we can write x, the solution to ax equals 0 pretty much, is going to be equal to x2 multiplied by 1/2 and 1. So null of a minus 5i is going to be equal to the span of this vector, and 1/2 comma 1. So any linear combination of that, otherwise stated, any scalar multiple of that is also an eigenvector. So let's take the eigenvector, multiply both of these by 2, and we get 1, 2. This is going to be the eigenvector that corresponds to lambda 1. So this has an eigenvector of that. And so this allows us to start to write P. So P is going to have the first column of 1, 2. That's going to correspond with the first column of D that has the eigenvalue there. Now we're going to repeat this process for lambda 2. So we still need to fill in these two. So lambda 2 is going to be equal to, we said it was 2 up here. So we're going to be finding null of A minus 2i. A minus 2i is going to be equal to 3 minus 2, 1, 2, and 4 minus 2. So 1, 2, and then the off diagonals were 1, 2. And we can quickly row reduce that. Instead of, basically we want AX equals 0. So we can go ahead and row reduce this. And we're going to get 1, 1 and 0, 0. Simply replacing the second column with -2 times the first column plus the second column. Let me go ahead and write actually the little squiggly line indicating row reduction. And so here we can write x1 equals -x2. And again, x2 equals x2. So we have that x is going to be equal to x2 times the vector -1, 1. So null of a minus 2i equals the span of this vector, -1, 1. And we'll go ahead and put that into our second column up here of p. -1, 1. And so now we've solved for p and we've solved for d. We could calculate p inverse, but to prove that we've diagonalized the matrix without calculating p inverse, we can say p is equal to, we said 1, 2, sorry, I'm reading columns now, -1, 1, and that d is equal to 5, 0, 0, 2. And what we want to say is that p, so that a equals p dp inverse. So let's multiply on the right on both sides. We have ap equals pd p inverse p. This is just the identity. So we have pd equals ap. And we can go ahead and solve for that and prove that ap times pd is equal to each other, or ap equals pd, and that will let us know that we've properly diagonalized the matrix. Sweet. Thanks for watching the video.